Good morning, everyone. Thank you all for coming. So it's my pleasure today to welcome Professor Seymour Spence from the University of Michigan as the speaker of our Warren Distinguished Lecture. Professor Seymour, as I said before, is a professor in the Department of Civil Environmental Engineering at the University of Michigan. But before joining the Department of Civil Environmental Engineering at Michigan, he was a research assistant professor at Notre Dame University. And his research is pretty much focused on several fields, including performance-based wind engineering, system-level analysis and optimization of certain dynamic systems, probabilistic modeling, uncertainty propagation, meta-modeling of static and dynamic systems, and more, including resilience adaptation of communities subjected to severe wind events. Professor Seymour also published more than 120 papers in his field. And he was also awarded with the NSF Career Award and also the J. James R. Cross Medal from the American Society of Civil Engineers. He is also an active member of some of the technical committees at EMI, including the Probabilistic Methods Committee. Thanks, Simon, and the floor is yours.
Okay. Well, thank you very much. Thank you, Kessin, for the introduction. All right, so with these slides, first actually I would like to just acknowledge being here at the University of Minnesota. It was an honor to be invited to give the Warren Lecture, and it's a pleasure to be here, being able to talk about some of the research I'm doing in my research lab with you all here at the University of Minnesota. It's my first time visiting, and I'm enjoying my time very much so far, so thank you very much for that. So, with today's talk, what I'm going to do is talk a little bit about some computational innovations in wind engineering towards reaching resiliency in urban environments. So, a quick outline for today's talk. So I will begin by talking about performance-based wind engineering, then I'll look at some methods we've developed in my research lab concerning machine learning and nonlinear dynamic systems, and then we'll look at modeling and simulation for resilient and adaptive cities, and we will conclude with a future outlook. So starting off with performance-based wind engineering, motivation for this comes from the massive damage and losses caused by extreme wind storms. Losses that are often in the billions of dollars for each extreme event. And limitations of current wind engineering practice are the following. We use excessive amount of material oftentimes, so this can be estimated to be as high as 15%. It also, prescriptive methods, how we do things today, stifles innovation because you're trying to satisfy all these prescriptions. And then there's no explicit pathway to obtain resiliency. You kind of follow all of these rules and you hope the system will have a certain amount of resiliency in it. So this is actually table 1.3-1 from the ASCE7, and it's useful to illustrate in a little bit more detail what I mean by prescriptive design. So if you go ahead and you design a system to resist extreme winds, you're going to go ahead and probably apply something like LRFD, and you're going to follow a number of rules, and you're going to satisfy these rules. Now, most of the rules are actually written in terms of limit states that are basically at the first yield point of the structural system. You then, by applying these rules, infer that if you were to carry out a probabilistic analysis or probabilistic assessment of that system, you would get these types of failure probabilities. But you don't explicitly do that. You infer it by following the rules, you get this. Moreover, when you look at ultimate load levels, you do not actually carry out assessments at these ultimate load levels, not explicitly. You infer that by satisfying these design limit states, you're going to also get satisfactory performance at the ultimate load level. This includes what these failure probabilities will be at these ultimate load levels. So the real idea with performance-based engineering in general, not just performance-based wind engineering, is to say, well, ultimately, this is where we want our system to actually behave correctly. So what we want to do is go ahead and explicitly model system performance at this ultimate load level. Now, if you're looking at a wind-excited system, as compared, for example, to a system subject to extreme seismic events, you actually do need to look at not just the structural system, but also the envelope system. And the envelope systems are rarely considered in classic prescriptive design or wind-excited systems. So you are working at this level. You are going to explicitly consider uncertainty because you're going to try and explicitly evaluate these failure probabilities. So if you want to carry out a performance-based engineering problem, you basically have to consider inelasticity in your analyses because you're now working at this ultimate load level, not the first yield. You're going to have to consider the envelope system if you're looking at wind-excited systems, and you're going to have to explicitly consider uncertainty if you are going to estimate these failure probabilities and therefore estimate metrics associated with losses and resiliency. So to be able to carry out something like this at these ultimate load levels, basically, well actually, before I get into how we were solving it, within my research lab we do have a kind of research thrust in this direction, and there's two main kind of areas we're looking at. So we wanted to advance computational models for enabling performance-based wind engineering chains, as well as develop holistic computational frameworks that define performance in terms of metrics that can be understood by technical and non-technical decision makers. So that was a couple of thrusts we have here, trying to get engineering solutions that can be understood by non-technical decision makers. So, all right, going back to what we were looking at here, if we want to carry out an assessment at this ultimate load level, considering uncertainty explicitly, what do we need to do? We basically need to solve some type of probabilistic integrals that looks something like this. What we're trying to actually estimate is the mean annual rate of exceeding a decision variable threshold of interest. That decision variable threshold probably going to be related to something like repair time, downtime, etc. Now to solve this, you need to create a model chain, and this is just an illustration of this model chain. Whereas these first models here are really characterizing your wind load as well as your wind environment, as well as any concurrent hazards such as wind-driven rain. Then we have these models, and this is all where the nonlinear modeling is going to come into play. So you're looking at nonlinear modeling of the structural system as well as the envelope systems. Once you've done that, you can actually go ahead and start estimating damage both to the envelope and to the structural system. Once you have your damages, you can then turn those into estimates of losses. Now, to be able to estimate this in a probabilistic sense, you always need to couch these type of model chains in some type of uncertainty propagation scheme so that you get probabilistic assessments of losses and performance. Now, we've been in my research lab creating various models for solving this model chain. I'm not going to go through them all. Just wanted to quickly highlight a few before we focus on models for carrying out the nonlinear modeling aspects. So we've developed Eulerian multiphase models for capturing concurrent wind-driven rain. We've created models based on bivariate copulars to describe the wind climates. We've also developed models that turn damages into losses. So we're not going to look at these models. What we're going to do in the next couple of slides, look a little bit more carefully at the models associated with the nonlinear modeling. So basically, if we look at the structural system, the nonlinear modeling is actually coming from solving a stochastic differential equation governing the dynamics of the system. What's occurring here is that we have uncertainties in the parameters, but one of the most important uncertainties is going to come in the form of the wind loads. That's actually a multivariate stochastic process. In particular, if you're looking at wind, you've got to capture what you see as the aerodynamic signature of the building. So to do that, so we're talking about things like vortex shedding, detached flow, very complex nonlinear phenomena. To capture that in a multivariate stochastic model, what you can use is spectral proportional decomposition, where you calibrate that model directly to what you're seeing in your wind tunnels. So the wind tunnels are picking up your detached flow and your vortex shedding. Now your spectral proportional decomposition can pick that up, and then your multivariate stochastic process model will also pick it up. Got to, in general, capture non-Gaussian features as well. Wind pressures are highly non-Gaussian. You can use data-driven translation models to do that. So you've got this representation of this stochastic process driving this nonlinear stochastic dynamics problem. Solving that gives you the nonlinear response of the system. However, as we mentioned, we are looking at the envelope system as well. And the envelope system from the outside is going to be excited again by these multivariate stochastic loads, which are going to be in terms of pressures. But as soon as you get an opening in your envelope, you get some damage, the internal pressures are also going to become dynamic. And to solve that, you've got to solve these equations for each opening. So if you write these equations for every opening you have in your envelope, you end up defining the following set of nonlinear system or nonlinear equations that you can solve using a fourth order Runcutter scheme or similar. So you're basically capturing the dynamics of the pressures inside as well as on the outside. This is also a stochastic process. One thing I would like to observe here is that in seismic engineering we have a distinction between demands and then damage. But you can immediately see here that now you've got these two coupled, because your internal pressures are going to depend on how much damage you have in your system. So as the damage changes, your demands are changing, and so forth. So you've actually got coupling here. All right, so we've got this kind of setup in terms of our dynamic response as well as our dynamic internal pressure response. We've got coupling in terms of damage and demands, but we also have coupling in terms of damage states themselves. Because if you think about an envelope component, which is subject to net pressure, it's also subject simultaneously to interstory drift. So if you get an interstory drift damage state, that will in general reduce the capacity of the system to resist net pressures. So those are coupled. So you've got coupling in terms of your damage states as well as demands and damages. To capture this, what we did was use these fragility models, these coupled progressive fragility models, where basically we have a set of fragility functions that gives the initial capacity of the system, and as soon as a coupled damage state occurs, we degenerate the fragility functions probabilistically to capture this coupling. All right, so this is how we're carrying out the nonlinear modeling. We add in all the models that I very briefly described in terms of the hazard, etc. And we've got everything we need to sort of set up a scheme to solve this probabilistic integral and get an estimate of the performance of the system. So we've got to get this mean annual rate of exceeding some threshold value of interest. Now, this is not an easy integral to solve, because for starters it's not twofold, it's very high dimensional because you've got to integrate over the space of the stochastic processes. So this is actually very high dimensional, and you're looking to estimate very small rates. Luckily our systems generally don't fail that often, so we do have small rates. Now to solve this, it's actually convenient to first just write it directly in terms of one's hazard intensity measures. So here we're kind of measuring the intensity of wind events with the maximum mean hourly wind speed at the site of interest, so that's going to give you our site-specific hazard curve. To capture wind directionality, we do need the complementary CDF of wind direction given wind speed, so that we capture that change in wind direction. That can come from your bivariate couplers that you've already calibrated to the site of interest. In addition, we have to recognize how virtually always when we have a really big wind event, a hurricane, we get a lot of rain. So we have a lot of wind-driven rain associated with these events as well. So you've got to use something associated with that hazard. Here we're looking at horizontal rainfall intensity during this event, so that's a concurrent hazard measure. Will in general depend on wind direction, wind speed as well this. However, from experimental data we've seen that this dependency is weak, so you can neglect it, which simplifies. Now to solve this integral, as we said in this form here, it's very high dimensional, and you're looking at small failure rates. So you can't solve it analytically, and you can't use Monte Carlo methods. What we did, we developed an approach based on stratification. It's very efficient. It was developed specifically for this type of problem. We'll look at this in a little bit more in detail a bit later on. But for now, we can solve this for small failure rates efficiently, not using too many samples. So let's just have a look at an example of what type of outputs we get when we run this type of problem. So this is a case study. There's a 45-story steel building located in Miami, Florida, and it's subject to this 1-hour wind event. We got some X-bracing on this system. The cladding system had 3,600 dual pane elements or components, which were laminated window panels. Those were what we were considering to be vulnerable to excessive net pressures and drifts. So we considered 3 damage states for each one of those 3,600 components. So we had 2 damage states which were induced by excessive interstory drift. First one, when you get some glass cracking, and then once you go past glass cracking, you start to get glass fallout. Then we had 1 damage state associated with glass blowout, just excessive net pressure causing the loss of the panel completely. These are the fragility functions, initial fragility functions associated with these damage states. Coupling, these are the expected loss in capacity between the damage states, in particular when one of these drift-induced damage states occurs as compared to the remaining capacity to resist, or the loss of capacity in terms of resisting net pressure. We also, in this assessment, these are the fragilities for your envelope system. You can consider the structural system as well. So for all of those components that you're not explicitly modeling in that finite element model of the structural system, you can use fragility functions. So here we're talking about things like your concentric X bracing, your base plates, your splices. This was buckling of these braces, so we were not explicitly modeling buckling in this model. Base plate splices are not there, so we use fragility functions to model their response. All right. So we set this up, that's our model. We ran this scheme. We're using 8,000 samples in total, so we ran 8,000 nonlinear time history analyses using stratified sampling to get these results. One of the things we observed, but we've observed this not just on this case study, we observed this on a lot of these structures we've looked at. When you look at classic first yield limit states, if you were to go ahead, satisfy your prescriptive rules, and you do your reliabilities, you just do not meet the reliabilities that are in table 1.3-1 of ASCE 7. You're always a little bit lower. Okay, so this is an ongoing concern. Historically, we know this occurs, but we just reconfirmed that effectively for us it was occurring as well. All right, so first yield, that's why you generally design. So your sum up here, what is this? This is the number of components that have yielded in your system. This is the mean annual rate of having at least one or more of these elements yielding. And you can see when you get first yield, you're somewhere here, which gives you this type of probabilities. So when you get down here, ultimate load levels, what's happening? That's where we want to be designing if you're doing performance-based engineering. You're down here somewhere. Those are the rates at which the ultimate load levels are occurring. This is what the structural system looks like in terms of yielded elements. So now you're at somewhere between 15 to 25% of your components have yielded once you get to these ultimate load levels under these extreme winds. And if you look at actually a little bit more in detail, you're getting other phenomena occurring as well, things like local buckling of your beams, etc. So there's a lot of inelasticity occurring once you get to these ultimate load levels, which is where we want to be designing in performance-based engineering. What about the cladding system? So we said we've got 3 damage states for each component of that cladding system. So these are the associated mean annual rates of having any one of the envelope components on this building enter into one of those damage states. So this is drift-induced damage state 1, glass cracking, drift-induced damage state 2, glass fallout, and this was loss of the panel due to excessive net pressures. This is all the mean annual rates of having these damage states as the final damage state at the end of the event. So you can see there is damage, net pressure is the predominant issue. However, you've got a non-negligible probability of having damage from drift from these systems as well. Now, we were looking at this coupling, etc. So we wanted to look at how important this was. So what we have here is the mean annual rate of having a certain number of components in one of these 2 drift-induced damage states. Right? So we've got 4 curves. So what are the differences between all these curves? This is damage state 1, so glass cracking. This is if you consider a linear elastic model and try and do your assessment of your cladding. This is if you consider a nonlinear model and do your assessment of your cladding. There's a big difference in damage. Indeed, you are going to underestimate your, you're going to have errors of up to 60% if you consider a linear elastic model and try and do these cladding assessments rather than a nonlinear model where you're generally getting larger displacements. And this is with respect to the pressure-induced damage state. And here what we're looking at is mean annual rate of having a certain number of components in this pressure-induced damage state. We've got various curves, but what we're interested in here is if we consider coupling, okay, between the drift-induced damage states, therefore causing loss of capacity against net pressure, or ignoring that. If we consider it, we're going to have, if we neglect it rather, we're going to have errors of up to 55% in trying to estimate when these damages are going to occur on our cladding. So we do need to consider the non-linearity in our structural systems. We do need to consider this coupling if we're going to get relatively accurate estimates of performance. Okay, once you've got all your damages, it's quite straightforward to transform the damages using your consequence functions into losses. This is the mean annual rate of exceeding a certain amount of repair cost in your system. You can go ahead and you can look at consequences of damage. So this is the mean annual rate of having a certain amount of volume of water entering into your system due to damage to the cladding system. You can deaggregate these any way you want, like one does in performance-based engineering. So this is just giving you understanding of where that water is coming from as you move up the building. So you can see it's predominantly coming in here at the bottom of the building. That may not be intuitive because you're looking at the building. So you've got larger drifts at the top. Why is it entering at the bottom? Water runoff So you've got water runoff down the system, and it's going to get into any openings at the bottom in a greater volume than it does at the top. So performance-based engineering allows one to do all of these types of assessments. Now, one thing we did mention, right, is that we're looking at ultimate load levels. So what happens if one says, all right, we had 25% of those systems, elements actually yielding and buckling? Why don't we do some explicit collapse analysis to see what's going on here? So to do that, at these ultimate load levels, you do need to capture complex system behavior, low cycle fatigue, fracture, buckling, etc. in your model. If you want to do collapse probabilities, you need to consider not only uncertainties in the stochastic loads, but you've also got to consider system uncertainty, which is going to be high dimensional because you've got a lot of material parameters throughout that system, and it's going to be partially correlated. The other difficulty is when you define collapse, collapse is not easily associated with one quantity of interest, and that makes it very hard to use existing variance reduction methods to estimate failure probabilities, because there's not one limit state you can really look at when you look at collapse of a system. You've got to look at it as a whole. So to solve this problem, we actually came up with what we called optimal stratified sampling. So the basic idea here is to take the failure probability and observe that you can take a sample space, you can choose a stratification variable, and you can go ahead and do a mutually exclusive and collectively exhaustive partitioning of your sample space. Once you've done that, using the total probability theorem, you can write the probability of failure, or the estimator of the probability of failure, as the probability or the stratum probability that multiplies the stratum conditional failure probability. Now, because this is a stratum conditional failure probability, which is this term here, that's not difficult to estimate. That's not a small probability. So you can estimate that using standard methods, while the stratum probability is not difficult to estimate either because you're not using any very intensive models to do that. Now, that stratification variable, it can be one of your input random variables, or it can be an output of an intermediate model, whatever is convenient. Basically, the idea is this: once you're stratified with respect to this kind of stratification variable, now you can decide where to put your samples, where to run your model. You don't need to run them where nothing is happening. So down here, or where you know what's going to happen, the system's going to collapse. You can run the samples where you've got abundant information, where you're on the fence between collapse and non-collapse. We went ahead with this estimator, we calculated its variance, which is a fundamental property of the quality of a estimator, and in particular we came up with the following convex optimization problem, which allows us to set target coefficients of variation on the probability failure estimator, and then optimally allocate our samples, our model runs, within the strata. So this means that we're optimally running our models in order to achieve a certain accuracy on the failure probabilities we're getting. So we can take a look at an example of this. So you can see it's not, for this approach doesn't rely on any quantities of interest. You're running the system, you can look at the entire system. So we went ahead, we wanted to get the failure probability or collapse probability of this system here. We took maximum wind speed in this case, so it wasn't an output of an intermediate model, it was just simply one of the random variables in the problem. We took maximum wind speed, we stratified with respect to that, 9 strata. We optimally allocated samples to get a coefficient of variation of 0.1 on collapse probabilities. So we ended up only having to use 1,000 samples to be able to get this collapse probability with this small coefficient of variation. This is the wind speed hazard curve, and this is where all the samples were being allocated. If you look at that in terms of wind rows, you can see all the samples are basically between 50 and 75 meters per second. That's why you're on the fence between collapse and non-collapse. That's where you want your samples. You don't need them down here, and you don't need them up here. So these were the results for that archetype structure, which was a 2D structure. Our collapse probability, as you can see, was coming out with a reliability of about 2.5, so pretty low for this, but it was a 2D structure, so it doesn't have the 3D action. But what was interesting here, we did end up with coefficient of variation of 0.1. So that was good, but this, as we said, is not reliant on a quantity of interest, so nothing is being sampled with respect to optimally and just one response parameter. We can just estimate any limit state we want within the system. So with the same sample set, you can get things like component first yield failure probabilities, system first yield, component buckling, fracture. You can look at all of these limit states and their associated probabilities. Also, this actually did allow us to shed light on how these types of systems collapse. These were steel structures. We can see in extreme winds, when you expect collapse to happen, you're getting fracture, you're getting yielding in your system, you're getting buckling in your system, and you're getting fracture. So you get all of these phenomena happening once these systems collapse. And of course, being a simulation-based scheme, you can create fragility surfaces if you want. So this was a probability of collapse, conditional on wind speed and direction. So you could see that 270 and 90 were the two directions where the system was particularly susceptible to collapse. We have taken a lot of these results and tried to get them into practice. So a lot of these results went into contributing to methods 1 and 3. These are procedures in the ASCE pre-standard for performance-based wind design. We've also created software to allow practicing engineers to try and run some of these types of analyses. This is called Wyra. It's freely downloadable right here, and it allows one to carry out nonlinear reliability analyses of these types of wind-excited systems and get these results and reliability indices. All right, so that kind of brings us to an end of our first topic. Here, what we're going to do is move on a little bit and start talking about how we can use machine learning to estimate nonlinear dynamic system response. So basically, motivation for this comes from how structural systems subject to extreme events, such as winds or earthquakes, will have these highly complex and nonlinear responses. If we want to characterize their performance in terms of performance-based engineering, as we saw, we do need to estimate probabilistic metrics. That means we need to propagate uncertainties through these complex, nonlinear, and dynamic structural systems. So we basically need to estimate stochastic dynamic response trajectories. So the program goals here, development of AI-based meta-modeling schemes for accelerating the evaluation of complex nonlinear stochastic dynamic systems, and then integration of these schemes into uncertainty propagation schemes. So those are the goals here. So let's take a look at how we're doing these, estimating these nonlinear response, nonlinear stochastic trajectories. So basic idea here is to recognize how a structural system can always be seen actually as a high-dimensional multi-input, multi-output system. You've got high-dimensional stochastic excitation on one side, high-dimensional stochastic output on the other side, and the structural model is just mapping between the two. So the first step in the approaches we developed is to define an associated reduced space with this. So this is just a reduced system. So you've got some reduced stochastic input, reduced stochastic output, which is related back to the original space through some type of coordinate transformation. But reduced order modeling, we've done, lots of people have done this in the past. The difficulty is, once you're in this reduced space, you generally have to go back to the high-fidelity space at each time step to evaluate the nonlinear forces. And that slows the whole process up a lot. So what we were interested in looking at is, can you learn the mapping in that reduced space using deep learning, so to avoid having to go back to the high-dimensional space. Okay, so to do this, first thing you need is this coordinate transformation. So in this work, we were actually using, or at least at the moment, we've moved on from this, but initially what we used were linear projection methods based on proper signal decomposition. So basically, you run your high-fidelity model for a few of these stochastic inputs, and you're going to be able to create what's called a snapshot matrix of responses from which you can go ahead and do a singular value decomposition, and then observing how in singular value decomposition, the first few orthogonal basis functions and singular values will contain the majority of energy of the system. You can effectively define a matrix for identifying a reduced space. Using a Glarkin projection, you can actually use the same coordinate transformation to define a relationship between the high-dimensional stochastic input and the low-dimensional stochastic input of the reduced model. So that's what we were going ahead and doing. So at this point, we've got a way of defining some reduced stochastic input, some reduced stochastic output. We want to learn the relationship between these two without returning to the high-dimensional space. Now, in reality, working directly in these is a very long time sequences. It's actually convenient to carry out an additional transformation. So you turn a time sequence into a sequence of wavelet coefficients. You do that for your reduced input and output. These are actually just going to be shorter sequences to learn, so they're easier to learn. So your deep learning neural networks are actually going to be trying to learn the relationship between wavelet coefficients of the input and the output. Now, this is a sequence-to-sequence learning problem. So basically, you do need to use some type of recurrent neural network, so therefore avoiding gradient exploding or vanishing problems. So the two which we're going to discuss in this presentation is the LSTM and a GRU. At the moment, we are actually looking at we've developed some physics-informed schemes for doing this, as well as looking at neural operators to do the same thing. But I'm going to discuss these two in this presentation. Before we can actually go ahead and look at prediction capability, you've got to train these models. So we developed an adaptive training scheme. So basically what we're going to do is run some samples, and then for each sample you can go ahead and you can define this weighted correlation coefficient, which is estimating the correlation between the predicted response of the meta model and the true response of your system. If you use k-fold cross-validation, you can actually get unbiased estimates of the mean of this over your training set, as well as its coefficient of variation. So you're getting an idea of how good that model quality is. So the higher the correlation, this weighted correlation coefficient is, simply got more correspondence between the true response and the predicted response from your deep learning scheme. So what we did when we developed our training schemes was simply set targets on the mean of this weighted correlation coefficient, as well as its coefficient of variation, and we kept adding samples until we reach those targets. Okay. All right, so let's take a look at a case study here. So we're looking at a 37-story steel moment resisting frame. We had a high fidelity model. It was developed in OpenSeas. It was a fiber-based model, 5 integration points per element. And we are going to consider 2 different models, and we'll look at the performance of these 2 models. The first model is a little simpler. So it's got elastic, perfectly plastic material behavior, small displacements. Second model was a little bit more challenging. So we're going to go ahead and have a Menegotto-Pinto material model, as well as large displacements. All right. So the uncertainties were stochastic wind loads blowing down the x direction. So you've got stochastic wind loads on this 2D frame acting in this direction. So you've got what's called a long wind response of this frame. Okay, let's have a look, once we've trained it, at the type of performances we get in trying to predict, using machine learning, the stochastic response trajectories of these nonlinear systems. So we're looking at horizontal displacement here at the top floor, in the x direction. So in blue, you've got the true high fidelity response to this stochastic excitation. So that's the true stochastic response trajectory of the system. You can see you start off at 0, this is a 10-minute excitation. You end up with a residual deformation of 1 meter. So this is a highly nonlinear system. The red dashed line is the prediction of that stochastic response trajectory using this meta model. You can see these are perfectly overlaid. So we're very easily predicting, or very accurately predicting, these stochastic response trajectories. This is the accumulation of error over time. It's basically flat, so you're getting no accumulation of error either. Now this is just one sample. You could say, well, you were lucky, you had one sample, it went well. What happened with all the other samples? So here, this was over all the samples of our training set. Horizontal here, we have the peak absolute response across the time history in terms of the reference model, and then we got the peak absolute responses that we got from our trained meta model. And we can see virtually all of these on the 1-1 line, so we're getting really good correspondence for all of these samples we looked at. And this allows us actually to directly estimate things like distributions of functions associated with your engineering demand parameters directly from these meta models, which are running at around 4 to 5 orders of magnitude faster than your nonlinear model. Basically, this will give you these nonlinear time history responses in less than 0.1 of a second once they're trained. It's like immediate. All right, this was model 1. What happens when we complicate the model a little bit? So now we've decided we've got a Menegotto-Pinto material model, and we've gone ahead and given large displacements as well. Now, if we look here, we can see this is exactly the same as what we had up here. We've got the peak absolute response, reference value, peak absolute response coming from the meta model. We've definitely lost some correspondence here. Indeed, if you go to your exceedance probabilities, these no longer match. You've definitely got a discrepancy. However, if you look here, so you look at this here, this is the stochastic response trajectory. Again, blue is the full model, dashed line is your LST or your meta model prediction. You're still getting an awful lot of good information, because that looks very similar. It's just not accurate enough to get the peaks, but it's a lot of information in here. So we were asking ourselves, how can we use all of this good information and correct for these discrepancies? So with that, we came up with this idea of implementing multi-fidelity Monte Carlo methods, where the low fidelity model is actually the meta model. Right? And the high fidelity model is going to be your true model. And if you're okay with not having a strictly unbiased estimator, what you can actually go ahead and do is estimate the high fidelity estimator of the failure probability directly from the training data you used for training your meta model. Over here, once it's trained, you can use any number of samples you want because it runs so fast. So the correction can be evaluated with any number of samples you want. Now, the tricky part here is this coefficient alpha sub I. That's our control variate coefficient, optimal value of which is given by this expression here, which requires the knowledge of the correlation coefficient between the indicator functions of the high fidelity and low fidelity estimators. So this is not actually easy to get. So what we were, and it's also dependent on the limit state you look at. So what we were suggesting in the work we've been doing, which is it's actually under review right now, is to go ahead and say, let's approximate this coefficient, this correlation coefficient between basically low and high fidelity model with that weighted correlation coefficient we defined in an unbiased fashion during training. So now we do have a value for that, and now we can easily evaluate this term and use this multi-fidelity estimator. All right, so let's go ahead and take a look at what we get. So these were these predictions, this cloud of predictions, where we're not getting particularly good accuracy. And again, it's the same distribution we saw on our previous slide. The red is the true value, dashed line is coming from the meta model with no correction. So if you go ahead and you look at the training data, obviously it's unbiased, but it's just very wobbly because you've only got 220 samples. If you go ahead and you do these multi-fidelity schemes, you get a really nice smooth line that has been corrected. Okay, it's been corrected from where we were here. And if you look at another response, this was top floor displacement at 37th floor. This is interstory drift at the top floor. You have a very similar situation. So you're being able to correct these results in terms of exceedance probabilities. This is just looking at, we just want to look at this. True failure probability here is about 0.024. If you only use the training data, because of how much it fluctuates, you're ending up with estimates around this order. If you use this multi-fidelity Monte Carlo based on only 220 high-fidelity samples, you're getting much results which are much closer to the target up here. In particular, you're basically using about 2% of the budget that would be necessary to run the high-fidelity model by using these multi-fidelity schemes. All right, so for the last few minutes, what I would like to do is look at one other trajectory or kind of thrust that I've been doing in my research lab, and that is modeling and simulation of resilient and adaptive cities. Now, the motivation for this comes from how, if you look at communities subject to hurricanes, you get a significant amount of losses, either 300 plus billion of losses over the past 10 years is being estimated. Obviously, thousands are left homeless in these events. These are the years, these are these catastrophic events. You can see in general they're increasing in time, so you're getting more of them. Now, if you look at this pie chart, you can see most costly insured losses, a lot of them are coming from hurricanes. So this is a big problem. This does represent a truly multi-hazard, multidisciplinary problem. So multi-hazard, you're looking at flooding, you're looking at wind damage, wind fields, you're looking at wind-driven rain. It's multidisciplinary because really to understand the impact of these things, you've got to look at engineering, but you've got to look at social science as well. So it's a complex problem to solve. So the program goals for this one was the development of distributed computing frameworks, enabling simulation of at disparate time scales and across disciplines. So you've got models running at different time scales, across different disciplines. We want them to interact. And then introduction of models and workflows for increasing the resiliency of communities to wind. We applied this framework, which was general, and we've been looking at applying it to wind. So the basic idea is to see the world as a social technical system. We want to develop a scalable and distributed simulation frameworks that allows researchers to basically link together any computational models they have for the various disciplines and then study, for example, like we did, the effects of interdependencies. This was the entire project team for this project. So we had a lot from civil engineering, but across different areas in civil engineering. And then we had a social scientist working on this project as well as a computer scientist. Basic kind of concept here was to develop what we called a runtime infrastructure. So this runtime infrastructure was basically around which we would do the distributed computing, allowed one, the idea was, to create simulators, which are basic models of certain components of an infrastructure. So you'd have your building simulators, bridge simulators, you've got your lifeline simulators. You've got simulators, if you so wish, of how people interact with all of your infrastructure. And all of these are communicating with one another through this runtime infrastructure. You also have in here simulators, for example, simulating extreme events like hurricanes. This was all written in Java, and we followed a publish-subscribe philosophy. And all the simulators were connected through some type of API. Okay, so that was the kind of idea. So what I would like to do is kind of illustrate how this worked for wind, because we did this for both wind and seismic events. So in wind, what we did, you would have this. So let's say you've got a simulator, so it's an input simulator. What it's going to do is going to publish to the RTI. So the RTI can be kind of visualized as this kind of channel with information flowing in time. So this would, for example, give information to the flow of information concerning the community layout, structural characteristics of the infrastructure components, how it can track and intensity. Then you can consider other simulators. There's a wind simulator that's going to be published to the community layout as well as the how it can track and intensity and publish information on the wind field. Then you have a pressure simulator, which is taking the wind field as well as the community layout and giving information on wind pressure on your infrastructure components and so forth. So all this information flows through here. It's all published, subscribed, and there's a time management system in there allowing one to step through the event. In the example I will show, we also had a resiliency simulator where we were looking at building recovery paths as well as community recovery paths. So this was basically subscribed to all the damage states of the infrastructure system, and then it was going to be publishing information on recovery. And then we housed all of this within an uncertainty quantification scheme so that we got probabilistic metrics as outputs again. So let's take a look at an example of where we applied this. This is a community in Miami. It had 513 buildings. We were very interested in what happened to people inside the buildings as damage occurred. So we were looking at population statistics. We ended up for the community we were looking at. We decided that it was reasonable to consider about 85% of the buildings occupied and about 15% vacant. This is the study region. This was the archetype of the residential building. We were also looking at a significant region around the study region, which will become clear a little bit later on. Okay, we considered two cases. We had this kind of as-built case, and then we had a case in which you took some mitigation strategies to try and enhance the resiliency of the system. So things like installation of windows and door penetration shutters. You had upgraded roof and wall sheathing nailing connections, increased wind resistance of roof shingles and wall covering, etc. So you got these two cases we were studying. We use a parametric hurricane model to create the tracks across Miami. We considered in the results I'll show you 15,000 hurricanes. So these are full tracks, so time evolving wind speed and direction as it moves through Miami. We, as I said, as a resiliency metric in this study, we were very interested in the housed population. So basically we're interested in this H here. This is how the number of people in a house recovers after the event. This is your housing capacity. This is your building recovery function. So once that gets back to 1, you're back to that housing capacity. So it all comes down to defining this building recovery function here. So here when we define this, we considered 5 different resiliency states. So damage states basically of the housing in our community. We had uncertain recovery time, so exactly how long it was going to take to get from one resiliency state to the next was uncertain. We also included uncertainty on whether the house population is going to evacuate or remain in there. That's a decision that varies between people. So if you have these for all of the buildings within your community, we aggregate them together and we can end up with our community level house population function. Okay? And then if we integrate, as shown here, we're going to get the resiliency associated with this metric. One thing I'd like to mention in these simulations we did, we had very high fidelity representation of debris. Right? So the debris here, we were using 3-dimensional 6-degree of freedom trajectory models. So in all the simulations we had, these debris which were being tracked individually within these communities, so millions of particles of debris inside the simulation. And one thing we were interested in observing is that a lot of the time you see these types of studies carried out and you have the target community. However, debris is flying. It's quite significant distances in extreme wind events. So we were curious as to whether the debris originating from outside the target community was having an effect on the damage states. These are all the debris, this is the heat map, all the debris hitting the buildings within the community, considering debris originating only inside the community. This was all the additional debris which were going to hit these buildings coming from outside the community. So you can see there's a significant amount of debris was coming in this corner here. This is because the wind direction in Miami is predominantly from southeast. So you get a lot of additional debris. So something we realized when we were doing these studies, you got to consider not the target community, but target community plus whatever's outside that target community. All right, so applying our framework, this is the type of results we were getting. These were community recovery curves. These were just broken up into from category 0 hurricanes, so the smallest, all the way up to a category 5. These are expected recovery curves. So again, we're using uncertainty, we're propagating uncertainty, so these are not just one scenario recovery functions, which you see an awful lot in literature. These were expected recovery curves over the entire uncertain space. And we can see, as we would expect, as the category of how I can increase these recovery curves started to move to the right, and it took longer. But because we were doing this in a probabilistic sense, we could also estimate the standard deviations associated with these curves. So these dashed lines here. You can only see 3 curves here because we just grouped together category 0 and 1 and category 2, 3 and category 4 and 5 events. And then you can see these dashed lines are giving you standard deviation. So where do you have the largest amount of uncertainty in these recovery curves? Right when you're in the middle of them. You've got a lot of uncertainty in exactly what that recovery is going to be. This is a metric associated with recovery. Here we're looking at the CDS curves for a state of 98% functionality recovery. So once we get to 98% recovery, what is the uncertainty in reaching 98% recovery? So we've got this in these 2 cases. We've got this as-built as well as those enhanced cases. And we've got all these different categories. But let's just look at these red curves here. Okay, so that's for the category 5 event. The dashed line is this uncertainty in the 98% recovery when you have an as-built scenario. So you can see if you're looking at about 50%, you're at about 450 days. If you consider the enhanced case, which is this solid red line here, you're going to reduce that to about 350 days. So it's making a difference of about 100 days in getting 98% recovery, functionality recovery. Okay? So you can see those mitigation plans have a noticeable effect. And then finally, these were expected resiliency metrics. Not much to say here, as you'd expect. As you get the category goes up, these go down. The difference in these kind of little bars here, you can see, is because this is for the enhanced case, this is for the as-built case. So again, those mitigation strategies do make a difference in terms of resiliency, but maybe not quite as much as one would expect, because those are the typical mitigation strategies actually carried out in Florida. So they did make a difference, but not that much of a difference. Okay, this is just a video we put together to illustrate all that debris we had in these simulations. So you can see all these little black objects. This is all the debris. There is actually a hurricane going by here. Our graphic artist unfortunately decided it was a nice sunny day, but this doesn't quite match what's happening here because we've got a category 5 hurricane going by. But these are actual debris objects within the community, and they were modeled using a physics model as we described. So we had millions of these debris objects in these simulations. It was all run in GPUs to be able to make these efficient enough. All right, the last thing I want to mention before I conclude here is we have taken these types of models and then incorporated the effects of water. So here we were looking at flooding as well as the effects of wind-driven rain. So again, using linear multi-phase models. We wanted to see the relative importance of the average depths of water inside the building coming from flooding, coming from wind-driven rain, where the water gets into a building due to wind-driven rain because of damage to the envelope. And this is just for a case study we did, Hurricane Harvey. We can see this is the inland flooding. This is the inundation depth on average across the community we're looking at. This black line is coming from flooding, actually what was observed in Hurricane Harvey. And all of these lines is the amount of water which would have got into those buildings if we were considering also wind-driven rain. And as you can see, as the category of winds goes up, you get a lot of water coming into that building, actually coming from the wind-driven rain, which is something which is often neglected. All right, a few concluding remarks. So I think that with these slides, hopefully, the potential of performance-based wind engineering to improve the performance of building systems subject to extreme winds was shown, as well as the role of computational modeling and uncertainty quantification in making performance-based wind engineering a reality. I think the potential of AI to speed up computation, particularly in predicting nonlinear stochastic response trajectories of these systems, was illustrated. And then the possibility of taking these kind of damage metrics and then taking them beyond a single building with those community-level simulations was also kind of illustrated. With that, I would like to thank all of the members of my research lab up here. There's a few, I think, which I don't have up there now, who have joined recently. And I'd like to obviously thank all the sponsors for this work, and I'll be happy to take any questions.
Thanks, Seymour. We are now open for questions.
I want to go back to section 2 in your meta model. I think I understood what you were doing, but my concern is, if we think from the point of view of a design engineer, it's going to come out, you're going to get a calculation of the probabilities, but they're not going to have any clue. Your model doesn't give them any information because it's so rarefied and obfuscated. They don't know where they need to tweak to try and improve that. And I could envision somebody just trying to have them randomly change something and then rerunning it in random. Have you tried any sort of the techniques for back propagation of machine learning models to try and identify critical components or critical areas?
So, I mean, the training is using the backpropagation scheme, right?
No, the back propagation isn't the right word.
Yeah,
It's the where you can take the output and try and figure out which.
So that's a.
Some sort of inverse analysis.
Yeah, so I would say that's a good question. And on any scheme such as machine learning, which is basically a data-driven model, as to know exactly what parameters need to be tuned which way, how many layers you need, exactly how you set that up is a complex problem. I don't know whether we're at a stage where we can have guidelines to be able to use these things independently. I think what we would like to do is build up methods that can work on a database of archetypical systems. And therefore, you end up having enough confidence that within that space of systems, it has the available tunable parameters and optimization algorithms to be able to solve that problem for a user. In training, one always gets the results between the target and the fitted model. And I think that is where a user doesn't have to know about how the model was tuned and optimized to be able to identify when it's not working and say, okay, I can't use this because it's not being able to predict those nonlinear stochastic response trajectories or time histories with sufficient accuracy. I'm not going to use it. I'm going to do a traditional method, just use my high-fidelity model. So there's an easy way an engineer can actually identify whether the model's working or not. Can we get the engineers educated to a level where they can actually start tuning parameters? Absolutely, but we need a sort of new generation of engineers that when they go through their master's degrees, they are being taught these topics, which is actually already occurring. So it is occurring where our graduate students and the graduate students across a lot of schools now are getting more and more subject to machine learning classes, understanding what machine learning is, understanding how to tune them. But there's always going to be a complex problem. It's a little bit like computational fluid dynamics. Computational fluid dynamics is incredible. You can simulate anything you want, but it's definitely not for a non-expert user. It's very hard. You really do need to know how to tune that model to get it to work. I think that's even harder than machine learning. I think machine learning and the concepts of machine learning are becoming more and more familiar with people. Just think about how we use ChatGPT. Does anybody check ChatGPT if it's giving the right answer? No, we just use it. Nobody knows what the large language machine behind that is actually doing, right? They're using it. But I think people are using it every day. It's as if we have CFD in our hands all the time. You become used to that concept. So I think as we move forward, we will be able to have these things in practice. But it's a completely valid point, which does have to be addressed at the level of education, as well as making people understand that you have a model, it's predicting something, you've got to check at least its predictive capabilities on your training set before being able to apply it.
Any other question?
Hi. Thanks for the wonderful presentation, Dr. Spence. I share quite a lot of common research interest in, so I'm particularly interested in the generalizability of the modeling. So I have very specific, first I would like to understand more how do you consider the pattern of the wind load. What specific wind load, how you consider in your model. And the second of all, as we know, a lot of hazard actually go to extreme events, which means sometimes the wind speed or is quite unpredictable, and I just want to know how the modeling system, how to work for this extreme case.
Okay, very good. It's a great question. So with respect to the wind loading, so let's just take the wind loading with a specified hazard intensity. So that what we do is we actually base the loading pattern on what we see in the wind tunnel. So you literally go into a wind tunnel, take your model, set up the surrounding buildings the way you believe they're going to be, the surroundings of that building you're kind of focusing on, and you're going to run that from multiple wind directions to get a complete understanding of how the wind loads are actually occurring on the building given a wind direction and wind speed. Right? So then we've got a very good idea of what's happening in terms of the aerodynamic phenomena. Then what we need to do is two extra steps. One is to understand that obviously the intensity of a wind event can be defined by some type of intensity parameter. One of the most commonly used is maximum mean hourly wind speed during the event at a certain height. So if you get a distribution function on your maximum mean hourly wind speeds, then you can associate the fact that in reality each one of those maximum wind speeds will have a different direction. You need to now get the copula. So I didn't have time to go through that. So basically you can define a joint probability density function of maximum mean hourly wind speed and direction at a site of interest. Those copulas should be extreme copulas, so you can then rely on extreme value theory and get what's happening in the tail of the distribution for your intensity parameters. Then you've got your wind tunnel data. You can use the wind tunnel data to calibrate stochastic wind load models so that now you can generate any number of realizations of those wind loads. So you're not just stuck with that one realization for the wind tunnel, which is not going to be compatible with nonlinear analysis, which is path dependent. So that's basically how we set that out. We've got intensity parameters, we do probabilistic analysis on those, extreme value analyses, and then we have wind tunnel data, which informs our stochastic, our multivariate stochastic models.
Thanks. Maybe you have time for one last question. Yes.
Thank you very much. I had a question about, you mentioned one of your group's aims was to how to communicate this to a non-technical audience.
Yes.
And so I was curious, when you show those visualizations at the end and how the modifications didn't make a huge difference in terms of initial damage, it increased the recovery time. I was curious, how would you tell that story to the public to kind of encourage those modifications? Are there scenarios where they were really effective, and how, I guess, how would you communicate that to a non-technical?
Okay, so that's a good question. So I had that point actually at the very beginning, and it was related to performance-based engineering. So the real goal of that was, lots of time when we do performance-based engineering, we get a little bit held up as engineers on the amount of energy dissipation we have in our system, or what's the detailing of the connection to ensure that it's going to survive this kind of level of ground shaking or wind event. But I think second generation performance-based design tries to get over that hump, and the idea is to say you can take all of those engineering solutions, the use of BRBs, the use of energy dissipation, and you can relate them to how does that affect the repair costs of your system over its lifespan. That for me is a metric that can be understood by a non-technical decision maker, for example a stakeholder. So that's what I meant really by that. Taking a solution, a very highly engineered solution, and relating it to reduction in downtime when a significant event occurs. With downtime, that equates to building being in operation, equates to profits. Repair costs, or low repair costs, equates to insurance premiums. So if I'm a stakeholder and I can work in terms of I'm investing in this and I'm reducing my insurance premiums and increasing the amount of time people are going to actually be in that building, that's actually showing me directly economically what the advantages of this highly engineered solution is, without me having to worry at all about you put BRBs in and increase the capacity of these components. So that's where we're trying to go. I think engineering in general always needs to go that way. If engineers want to be at the decision-making table, we've got to stop talking about engineering and start talking about how does that actually affect the decision-makers' solutions. They're not going to be so worried about what you're doing. It's just how does it actually affect their portfolio of investments. So if they see, I'll pay more for this engineered solution because it has a good long-term benefit to me, I'm going to pay for the engineered solution. It's a no-brainer. But if I can't understand the benefit of it, then I'm probably just going to go for the cheaper option.
Right, thanks. We are concluding now, but thanks a lot, Simon, for your presentation. That was great.